Hi, I'm Alan. I'm with Nervos, and I'll be presenting Eaglesong today, which is the proof of work hash function. This is joint work with a former colleague of mine, Tomer Ashur. So this is an overview of my talk. First, I'll be talking about the motivation for having a proof of work function in the first place and for having a new one, different from Bitcoin. And then I'll talk briefly about the very generic recipes for cooking up a hash function. Then I'll delve a little bit deeper into the specific design choices that went into Eaglesong, after which I'll cover briefly the analysis we did to assess the security of this hash function. So, proof of work. Nervos is a distributed peer-to-peer decentralized network. Anyone can join, anyone can leave, and somehow all these nodes agree on a state of history of who owns how many coins. And when they speak to each other, anyone can lie. And that's an important obstacle because this immediately means that a Sybil attack is possible. In a Sybil attack, an attacker floods the network with dummy nodes who lie, who join, or who don't respond as however the attacker indicates. And the question, whenever someone presents a decentralized network, is how do you prevent it from being Sybil attacked? And there are basically two solutions, and one is to drop decentralization. We require from a central authority signatures, and then any node who has a valid signature is a valid node, and any node who doesn't have such a signature just cannot participate. On the other hand, a decentralized solution can be obtained via proof of work. Here, every node provides a proof that they are expending energy in order to participate in the network. And this doesn't kill the Sybil attack per se, it just makes it expensive. Under the assumption that enough mining power is honest, this is a secure solution. So the circle of life is rather similar to what Matt showed. It shows the context in which proof of work is necessary. So we want a secure payment system for other things to make the cryptocurrency valuable. We want the cryptocurrency to be valuable for other things perhaps, but also to incentivize miners. Why do we want to incentivize miners? We want them to work on extending the blockchain. Why do we want them to work on extending the blockchain? Well, that's what makes the blockchain secure, what makes attacks infeasible, and so on. So if you're going to design a new cryptocurrency, you have to find a way to make the circle complete. And this is exactly where proof of work comes into play. Proof of work is what miners do to extend the blockchain and make an attack on it infeasible. So let's sit and think for a while, what are the desirable properties of a proof of work function? Firstly, hard to solve can come to mind, but it doesn't really capture what you want. What you really want is tunable hardness because, well, in traditional Bitcoin, the block rate is supposed to be 10 minutes per block, roughly on expectation. Nervos has a more intelligent solution optimizing bandwidth usage, but there has to be a way to regulate how difficult it is to solve the problem as a function of network circumstances. Next is easy to verify. You want every node on the network to be able to verify that a proof of work puzzle has been solved, independently of whether they are a large server farm or small nodes running on a Raspberry Pi or an Apple iWatch. In principle, in fact, you want it to be fast and require little memory to verify. Next, you want it to be friendly to decentralization, and this is rather difficult because it has to be friendly to decentralization immediately after network launch, but also in the long time. And you want the barrier to entry to be as small as possible, because that can remove disincentives of as many people as possible to join the network. And if they do, then you have a decentralized network, or at least a better argument for having one. We want the proof of work function to be fair, meaning that in principle, the mining rewards are distributed in proportion to the shares of computational power that are actually working to secure the network. So if you have an optimization that you keep secret, we don't want that to happen, because then you're getting rewards that are not in proportion to the power expenditure. And the same is true if you know a different function, but that's easy to compute and that agrees on most of the outputs. If you're going to mine that instead, you can still make a profit net, and we don't want that either. And a third point here is we want to make an as sound as possible argument, as strong as possible argument, that we don't know a backdoor into this function. This last point was very important. So if we're going to look at how Bitcoin achieves these properties, they have check marks all over the board. And that's really cool. Bitcoin uses twice iterated SHA-2, which is a well-known hash algorithm, and Nervos might consider copying Bitcoin in this proven successful method, but you'll soon figure out that there are two problems, or rather one problem. It's not really friendly. Using SHA-2 is not really a good idea with decentralization in mind, because there is a lot of existing Bitcoin mining hardware that will completely swamp miners if Nervos becomes too successful. So motivated by this, we need something else. So first of all, we want to make existing mining hardware obsolete. So that means we have to find a new function. And we can't just take Blake or any other existing hash function, because ASICs may have already been developed for them. The only way to guarantee that hardware does not exist is by designing a new function. Secondly, we want this function to be easy. This lowers the barrier to entry, and this makes verification fast. So it's easy to implement, easy to explain, even to someone who does not hold a PhD in cryptography. Simple, in other words. And thirdly, we want it to be fair. Mining rewards are distributed in proportion to contributed mining power. That boils down to the three properties mentioned earlier: optimization-free, approximation-free, and backdoor-free. And in cryptographic terms, this means we want a secure hash function. And, well, we actually want a secure proof of work function, but if it's not simultaneously a secure hash function, then that distinction might indicate a weakness. And we want to convince you, most of all, that there is no weakness because there is no backdoor. So basically, this means we have to develop a complete cryptographically secure hash function. So how do you do this? In broad terms, the first rule of hash function design can be summarized in 4 letters and 1 punctuation mark. Don't. It's very tricky. You have to take into account many things. It took experts years to become an expert, and it's easy to overlook pitfalls, and it's difficult to do it securely. And if you make a tiny mistake, it can cost a lot of money. This rule is comparable to the first rule of rolling your own crypto. The first rule of protocol design, and of course, don't do a PhD either. If you're really, really stubborn and also smart, maybe you can risk doing this. So in principle, the difficulty of hash function design rests in designing and analyzing the design and based on that analysis, redesigning. There are a couple of choices, but having made such a choice from these spaces of choices, so first we choose a set of operations that can be run on your CPU or even your programming language. That gives you an operation set, and then you choose how to compile these operations into a network or a topology that outputs a permutation, either permutation or pseudo-random permutation. There's an easy way to transfer one into the other. And with a permutation, it's really easy to get a hash function. You just use one of these standard techniques. What we want is the permutation to be secure. So the question really is, how do you go from an operation set using a network into a permutation? So in terms of operations, there are plenty of options, mostly provided by standard arithmetic operations. It's worthwhile noting that we have multiplication and inversion in extension fields match XOR, and XOR is really, really cheap. And based on that, AES was built. So AES uses XOR, multiplication, and inversion in extension fields in binary fields, in fact. But by no means are new ciphers limited to the same choice as AES. For instance, DES, which actually came earlier, uses XOR and lookup tables. SHA-2 uses a whole bunch of operations. Ketchak uses some fewer. Blake uses 3 operations: addition, rotation, and XOR. And this is actually a very, very, very popular choice called ARX. And Eaglesong has made the same choice. We are also using addition, rotation, and multiplication. Eaglesong is therefore an ARX hash function. So in terms of network types or network topologies, there are really 3 categories, of which 2 are proper categories, and the third one is the remainder category. So firstly, we have Feistel networks. And this is a way to, technically speaking, turn a one-way function like f into a permutation, but it can also work to make a weakly secure function into a strongly secure function by iterating this many times. And you can easily see that this is a permutation, because if you just take the same network and append it down, except you skip one of the wire flips, then you get exactly the inversion operation. This was chosen by DES, but DES has since been rendered obsolete by the substitution permutation network. In this case, you have strong but local functions called S-boxes alternated by weakly, in fact, linear permutations across the entire state. And this is the strategy used by AES, which has all but replaced DES. And by no means are you limited to one of these choices. You can paste building blocks wherever you like, but it might make your network more difficult to reason about. I could not classify SHA-2 as one of the first 2 types, so I classified SHA-2 as the third type. Based on being able to reason about the network and its properties, we went for AES's substitution permutation network because it enables the wide trail argument. And I'll get into the wide trail argument in the last few slides of my presentation, because it has to do with how do you build an argument for security, or rather, how do you build an argument to show that a particular attack is sufficiently infeasible. So after you have decided, after you've chosen your network and you've produced sufficiently strong permutation, then the question is, how do you turn that permutation into a hash function? And there are basically two options, of which the first is Merkle-Damgard. In Merkle-Damgard, you split your message into many chunks, and starting from a random chaining value, you apply a compression function for every chunk. This results in a single fixed length output, and you can show that if you can find a collision of your hash function, that necessarily implies a collision for one of the compression functions. Therefore, if you have a secure compression function, you also have a secure hash function. Well, then the question is, we don't have a secure compression function, we only have a permutation. Well, cheating slightly, if you have a pseudo-random permutation E, then you can easily make a compression function using either the Davies-Meyer or Miyaguchi-Preneel structures. The little triangle indicates the key interface, which is the property that distinguishes permutation from a pseudo-random permutation. So option 2 for the mode of operation is the sponge construction. In this case, you have R bits that represent the rate and C bits that represent the capacity, and R plus C is the size of the state, and we have a permutation that applies to the entire state. Like in the Merkle-Damgard strategy, your message is split into multiple chunks, and in every iteration, the chunk is XORed into the rate part of your state, and then a permutation is applied until there are no more chunks left. That's the absorbing phase, and then in the squeezing phase, you just read out the rate part of your state and then apply the permutation again. This gives rise to hash functions with an arbitrary output length, but you can truncate those to any length you desire, including a fixed length. This is the mode of operation that Ketchak uses, and probably the reason why they won the SHA-3 competition, which was, after all, looking for new and improved ways to build hash functions. And we liked the elegance of this construction, so Eaglesong chooses to adopt a sponge construction also. So that's the high-level design choices. Now let's get into closer detail. Eaglesong consists of 16 words of 32 bits each. These are just represented as integers on your average CPU. It consists of 43 rounds repeating 4 steps, which are the following. We have between word diffusion, we have within word diffusion, injection of constants, and nonlinear layer. I'll get into each of these steps in a second. Just this diagram represents the round function, and by repeating this 43 times, you get the permutation, and by plugging the permutation into the sponge framework, that's how you get the hash function. So the between word diffusion operates based on a bit matrix, this bit matrix, and we find the next state by multiplying the old state with this matrix. And for some reason, coding theorists imagine that row vectors exist, and they like to multiply row vectors by matrices rather than the much more natural matrices times column vectors. The reason why we adopted row vector notation is because we pay homage to the coding theorists in using the white trail argument. And the origin for this white trail argument and for this homage is, of course, that there is a correspondence between the white trail argument and coding theory, and this correspondence pops its head because this matrix has been chosen because it corresponds to the rightmost part of a BCH code with these parameters, except for the last column that has been chosen as the unique kernel of the matrix on the left. So that was between word diffusion. How about within word diffusion? We noticed that rotation can be described mathematically as multiplication by a monomial in this ring. So we asked, what other things can you do in this ring that still preserve the property of transformations to permute their inputs rather than send multiple inputs to the same output? And the clue is, this is a ring, and whenever you multiply with a unit from the ring, that's a permutation. So you cannot multiply with pairs, or rather sums of two elements, two monomials, but as soon as you have three monomials, that's a unit, and you can multiply by this, and you can find an inverse of this element in that ring. So that's a beautiful mathematical description, but what does it mean concretely? Well, it means that by performing two XORs and two rotations, you get this beautiful mathematical relation, basically for free and still using ARX operations. You might ask the question, okay, but where do we get the A's and the B's from? They were obtained using shake, seeded with a quote by Claude Shannon. The third step is the injection of constants, and that's really, really very simple, because in this step, every state element is XORed with a given constant that is unique for that state element and that round. So for every state element, we have this microtopology. These constants were found by expanding shake after seeding it with a quote by Friedrich Hayek. But importantly, our security argument does not rely on the presence or on the distinction of these constants. The last layer is the only nonlinear layer, and this consists of an addition, two rotations, and an addition, laid out as follows. We first add the right element to the left, then we rotate both elements in opposite directions by 8 bytes, and then we add the left element to the right. This is also very simple, and this is the only step in the 4 steps of the round function that involves additions. Since addition is the only nonlinear element, the analysis of this network is crucial. So let's get into this analysis. First of all, we have to understand, what does an attack mean? And from the point of view of designers of cryptography, an attack is any property, any algorithm that allows you to distinguish the function being attacked from a random one. And we actually focus on distinguishing the permutation of Eaglesong from a random permutation. And if you think, well, technically there cannot be such a thing as a random permutation because you can always hard code your permutation in your Turing machine that attacks it, well, yeah, but we have an argument to lift a given permutation to pseudo-random permutation based on modifying the constants So that's one of the reasons why I said our argument does not rely on those constants being fixed. So there are a couple of branches, families of attacks, and firstly there are structural attacks. These exploit weaknesses in your network topology. For instance, if your network reuses the same subnetwork in multiple locations, then you can trick the cipher into computing the part of the network in one location while it's actually performing the part of part of the network in another location, and then attack a simpler cipher than you would otherwise be attacking. In algebraic attacks, we look at descriptions of the function in terms of only addition and multiplication, and there are a couple of algebraic rewriting tools that can help in expanding those representations. And in statistical attacks, you look for properties or invariants that propagate throughout the cipher with a certain probability. And if the probability is high enough, you can compose these local properties into global properties and then test the function in sufficiently many inputs to determine whether it does or does not satisfy this identified statistical anomaly. For structural attacks, we do use distinct constants, and that makes a self-similarity attack difficult. And also we use the substitution permutation network topology. If it's impossible to completely rule out a structural attack, but certainly if someone were to find a structural attack, with overwhelming likelihood, it would also apply to generic substitution permutation networks, and that would be a very big breakthrough result in cryptanalysis. For algebraic attacks, we rely on the fact that ARX ciphers do not arithmetize well. What I mean by arithmetize is it is very difficult to express addition in particular as a function over the binary field. You can do it, but this expression will be huge, and if you then take into account a full expression of the hash function with all 43 rounds, this expression will explode, and you will not have enough memory to store a full expression of this hash function, let alone evaluate it anywhere. The statistical attacks are the relevant ones for basically all ARX ciphers, and that's exactly what we are focusing on. In fact, differential and linear cryptanalysis are the most important attacks, and almost the entirety of symmetric cryptanalysis focuses on either differential or linear cryptanalysis with some room for variance. Rotational cryptanalysis is relevant specifically in the context of ARX ciphers and does not generalize well to alternative operation sets. So, differential cryptanalysis studies the propagation of differences throughout the ciphers or its constituent components. So instead of looking at an input X goes to an output Y, we look at two inputs, X0 and X1, and we look at the difference made by their corresponding outputs. This is interesting because linear functions preserve differences, or they might send some differences to other differences, but if you know that a particular difference is entering a linear function, then you know that certainly that same or another difference is exiting that function. On the other hand, or the reason why you know this is because it is a linear operation that applies to the difference just as easily. On the other hand, if you have a nonlinear operation, the same is not necessarily true. You could have an input difference that gets mapped to one output difference or to another output difference depending on circumstances. And that's an interesting property that you need, because it can be qualified in terms of probabilities. And for a random function, we know this probability, and it is really, really small. It is essentially the size, 2 to the minus size of output. So we want to design a network of operations such that the maximum expected differential probability is very close to 2 to the minus size of output. In our case, our Eaglesong's output length is 256 bits, but we only claim a security level of 2 to the 128, meaning that we're okay with 2 to the 128, 2 to the minus 128. We don't quite have to get that low. So the question is, how do you compose, or how do you argue that a given network actually achieves such a very good differential probability? And the way you do that is you decompose F into its constituent components, and you analyze these components separately. So let's do that. We have the diagram of our round function, and the first 3 steps were linear. And linear doesn't do anything for differential cryptanalysis. That's why differential cryptanalysis is useful. What does do something for differential cryptanalysis is nonlinear steps. So in particular, it's the addition, rotation, addition block that is going to give us our sought after maximum expected differential probability degradation. So we notice that there are 3 classes of events relating to this block. Firstly, we have a good event, in which case an incoming difference or an outgoing difference is associated with a degradation of 1/4 or more, less. In a bad event, the degradation is not quite as striking. And thirdly, you can consider 0 differences, either entering or exiting. In those cases, you don't get to multiply anything into your probability, and you don't get any degradation as a result. We are using the argument that if there are bad events in some places, then in other places there have to be good events. And that's obvious if you consider the fact that we repeat the round function, meaning that immediately before one round function, there was another layer of addition, rotation, addition blocks. And this moves into the wide trail argument. It shows that, or rather, in our case, we ran experiments, and we can conclusively tell you that in any 2 rounds, at least 5 ARA blocks are active, and at least 2 of them are strongly active, having the degradation of 1/4 or less. Well, this allows you to upper bound the maximum expected differential probability of the entire thing. So the entire function is described as n/2 pairs of rounds, and in every round we have at least 5 active, of which at least 2 are strongly active. That's where all these numbers come from. That gives us a bound, and we have to choose the number of rounds such that this probability will be close to 2 to the minus 128. That's differential cryptanalysis. Linear cryptanalysis is rather similar. Instead of studying the propagation of differences, we now study the propagation of satisfying masks. What is a satisfying mask? It is a satisfying mask to an input X and an output Y is a pair AB such that the inner product of X and A equals the inner product of Y and B. This is just another way of writing equals in binary fields. So they can both be 0 or they can both be 1. This has the same property that linear functions always come with a satisfying mask. A satisfying mask going into a linear function always had a satisfying mask coming out, and you can see this through rather simple algebraic manipulation. It gets interesting when you have a nonlinear function, because once again, you can have an incoming mask that gets mapped onto one outgoing mask or onto another, depending on circumstances. And then there's a certain probability related to which particular choice occurs. And this probability, well, we square things and then rename things into potential. This maximum expected linear potential is exactly known for random functions. So we want the concrete function's maximum expected linear probability to be as close as possible to this 2 to the minus size of y. And the way we make this argument complete is we decompose f and study its constituent components. Once again, we view the circuit topology, and we observe that only the nonlinear part has any relevance for linear cryptanalysis, which is once again the ARA layer. And we observe 2 types of events, good events and bad events. In good events, the degradation is 1/4, and in bad events, there is no degradation at all. We exhaustively list 4 bad events that are non-zero masks, and of course there's also the 0 mask. That moves to another iteration of the argument that bad events in some places necessarily come with good events in other places. In particular, if there are bad events at the bottom of this diagram, then there have to be good events at the top, or the other way around. We can iterate over all possibilities of all sequences of bad events and good events, and we reach this particular wide trail argument. In any 2 rounds, at least 3 ARA blocks are active. This follows from computer experiments. Well, this immediately leads to a bound on the maximum expected linear potential. We have n/2 pairs of rounds, and in every such pair, at least 3 ARA blocks are active. This is actually the bottleneck. So if you compute 2 to the minus 6 times n equals 43 over 2, that is exactly 2 to the minus 128, which is 2 to the minus 129, which is 1 bit in excess of our security level. Lastly, there is rotational cryptanalysis, and this is slightly different. Instead of studying linear properties, we study the propagation, not of differences, not of satisfying masks, but of pairs of inputs that are rotational pairs. A rotational pair is just x and x bar, such that you get x bar by rotating x by any given amount, although it has to be the same amount throughout your entire analysis. Unlike differential and linear cryptanalysis, it's not generally true that linear functions map rotational pairs to rotational pairs. So that's interesting. We have a property that's no longer works well with generic linear operations. It is true that when you XOR, rotational pairs are sent to rotational pairs, and when you rotate, rotational pairs are sent to rotational pairs. And when you add, rotational pairs are sent to rotational pairs with a certain probability, which can be leveraged to induce sufficient degradation. And in fact, that's what Eaglesong does, or rather, that's the argument that Eaglesong uses for security. We assume that every addition occurring throughout the entire network is independent, and we counted the number of additions, so we just raise this singular degradation to the number of additions occurring in our network. That's the argument Eaglesong makes, but other ARX ciphers, they make the argument based on the addition of fixed constants. When you add in fixed constants, you break rotational pairs with overwhelming probability. It has to be a really, really crappy constant in order for it to not break the propagation of rotational pairs. So this is one aspect in which our analysis differs from traditional ARX analysis. This allows us to make an argument about using different constants to consider an attack on pseudo-random permutations rather than a random permutation. This also allows us to switch out the seed in our Ketchak expander to obtain different constants between the paper and the RFC. Thank you very much for your attention. I'll open the floor now for questions.